Newton's law of universal gravitation is expressed as an equation. It says force can be calculated as long as you know the mass of two objects that are attracting one another, as well as the distance from center to center between the two objects. But force is a vector quantity, so the left side of the equation has the symbol that shows that force is a vector. I don't see anything that's a vector quantity on the right side of the equation. Mass is a scalar quantity. Well, let's see. If we make an axis starting from the center of the Earth and just pointing directly outward away from the center, and that axis doesn't point straight up, doesn't point directly to the right, so instead of calling it x or y, we'll say that's the radial axis. A vector that's exactly 1 unit long, if this purple vector represents a vector 1 unit, if it's 1 unit along the r-axis, then that vector has the symbol r hat. And because it has a magnitude of just 1, I can multiply r hat by any quantity and not change its magnitude. So actually the full expression for Newton's law of universal gravitation is the one we see on the left with r hat added to it. So by multiplying by r hat, you're not changing the magnitude of the overall calculation. All you're doing essentially is finding a way to give direction, and the force always lies along the direction. Actually, the radial vector points outward, so the truth is we need to put a negative sign in this equation, because if we have two masses, mass 1 being the Earth and mass 2 maybe being some satellite of the Earth, could be the moon or any other man-made satellite, then the force doesn't point outward in the direction of the vector r hat. The force acting on mass number 2 points inward, opposite the direction of this vector r hat, hence the negative sign. Okay, but we also know there's this shortcut for finding force. We can say F equals mg. So this symbol g we recognize as acceleration due to gravity, but as I stated in our last video lesson, it's probably best we start referring to g as gravitational field strength. So the only way these two equations can mean the same thing is if g is everything but one of the m's in this equation. So gravitational field strength must be g times one of the two mass quantities divided by r squared. And then to make the right side of the equation a vector quantity, I'm going to multiply it by 1, or excuse me, I'm going to multiply it by a vector equal to 1, but that vector lies along the r-axis, and because it's exactly 1 unit, we put that symbol hat. So there we go. This is a way to calculate gravitational field strength. Now you might have a question about which m is which. Well, either way, the force acting on object number 1, which in this case is the Earth, would be equal to the mass of the Earth multiplied by the gravitational field that exists all around mass number 2. And likewise, the force acting on object number 2, which in this case is the satellite, would be equal to the mass of the satellite multiplied by the gravitational field created by the Earth. And these two forces must be equal and opposite. That's according to Newton's third law, right? Okay. So maybe we can picture this gravitational field. Imagine taking a very small amount of mass, maybe something, not even 1 kilogram, 1/10 of a kilogram, 1/100th, 1 gram, and placing it here, well above the surface of the Earth, and releasing it from rest. Then we know it's going to want to accelerate downward. So we can draw a line pointing downward that just shows what the direction of force would be if the object were placed at this position. If I put the object over here, then it's going to want to accelerate in that direction. So I can imagine testing the Earth's gravitational field by releasing a small massive object from rest and seeing in what direction it accelerates or in what direction force is exerted on it. So thinking of it this way, I can actually picture the Earth's gravitational field as a set of lines that all point radially inward toward the center of the Earth. I want you to notice something about this pattern of lines that emerges. There's some sort of symmetry to it, but this does represent a non-uniform field. Uniform fields, in contrast, look like this. For a field to be uniform, all the lines in that field have to point in the same direction. In other words, all the lines that represent the gravitational field need to be parallel to each other, and the spacing between the lines needs to be the same at every point. So, for example, in the physics classroom, if we tried to test once again, what's the gravitational field inside of a physics classroom, we could drop an object, grab a coin out of our pocket, let that be what we call our test mass, the object that's going to respond to the field. And of course, it's going to accelerate straight down. It's going to experience a force that pulls it directly downward, and we drop the penny from this part of the classroom straight downward. And so this is how we can get a set of gravitational field lines inside the classroom that are all parallel to one another and evenly spaced. But of course, this represents a narrow view of the Earth. The ground appears to be flat, but if we scale down this drawing, and we shrink it and shrink it and shrink it and shrink it, we actually notice that the classroom is part of the curved Earth, and what we thought was a uniform field was really just the effect of restricting our view of gravitational field to a small region. But the gravitational field, in all actuality, points toward the center of the Earth. So, the Earth's gravitational field might appear to be uniform in a local region near the surface of the Earth, but when viewed far afield, we see that the Earth's gravitational field is non-uniform. So the strength of the field is indicated by the density of the field lines. Meaning, at some point here, right near the surface of the Earth, the field lines are separated by a small distance. If you work your way farther out, then the distance from one field line to the next becomes much larger. So each of these circular lines I'm drawing represents regions of constant elevation, and those regions sit perpendicular to the field lines. And you can move an object along any of these circular paths and not do any net amount of work, because the force would be at all points perpendicular to the displacement if the path was restricted to this circular path. But if you want to move an object from elevation A, if you want to move an object from elevation A to elevation B, regardless of the path taken, whether the object directly moves up in elevation from A to B, or if the object, for whatever reason, does a loop-de-loop and goes up and down and spirals around and then ends up at elevation level B, the same amount of work would be done in this case or in this case. So we say work done by a gravitational field is a conservative type of work. It's path independent. Well, we know the value of the gravitational field at the surface of the Earth. At the surface, gravitational field strength, G, is about 9.8 newtons per kilogram. And the equation is gravitational field strength is universal constant multiplied by mass divided by distance squared. Now, if I want it as a vector, I got to throw in the r hat. If I'm just looking for magnitude, then I can leave the r hat out of the expression. So you can see that just like force is an inverse squared law, gravitational field is also an inverse squared law. That means if we double the distance, if the field strength at a distance from the center of the Earth of capital R is equal to 9.8, then at a distance of 2R, the field strength should be not just 1/2, but 1/4 of 9.8, which should give us approximately 2.5 newtons per kilogram. If you're interested in the gravitational field strength at a distance of 1, 2, 3R, at that point, gravitational field isn't just 1/3, rather it's 1/9 of 9.8, or about 1.1 newtons per kilogram, and on we go. I think a graph of the gravitational field strength compared with distance from the center of the Earth would look something like, well, let's see. Let's put a special value along this axis of capital R, say that's the radius of the Earth. Well, it doesn't really make any sense to provide any information for that region of the graph here, because I don't see how we're going to ever place an object in orbit within the surface of the Earth. So it's only at points beyond lowercase r greater than capital R that are of any importance to us. So right at the surface, when the distance from the center happens to be the radius of the Earth itself, then the value of g is equal to 9.8 newtons per kilogram. So there's one data point. And from there it seems to drop off. At 2r, it doesn't just go down to half, but it goes down to 1/4 that value. At 3r, it doesn't go down to 1/3, it actually goes down to 1/9 of that value. So this is a curve that rapidly drops off and approaches 0, but never actually hits 0. So the question is, how far away would you have to get from the Earth in order to no longer be in its gravitational field? And the answer is only as r approaches an infinite value would the gravitational field strength ever drop to 0. So there's a relatively quick introduction to what we mean when we talk about gravitational field. The equation for gravitational force relies on two masses, because gravitational force is a sort of interaction. But any object by itself has a gravitational field all around it. Every planet creates a gravitational field. You have a gravitational field around you, although your gravitational field is very weak compared to the Earth's gravitational field. Gravitational field depends on the mass of the object that creates that gravitational field. And the farther you get from the center of the object, the weaker its gravitational field becomes.